Good morning, students. Today we have lecture number 8. Lecture number 8. So far we have studied about the electric potential and potential difference. Electric potential, potential difference, potential energy of system of charges, and relation between electric potential and electric field intensity. Now we shall solve some numericals related to lecture number 4, 5 and 6. 5, 6 and 7 related to lecture number 5, 6 and 7. Okay. So take pen and paper and start writing the numerical. So this is one numerical. Start writing. Write this numerical. I will not write on the board. You write on the paper and we will solve like in the classroom. There is no any problem. Okay. So simple problems. First I will solve 1 or 2 problems. Okay, write down. If the potential in the region of space around the point, if the potential in the region of space around the point, if the potential in the region of space around the point, if the potential in the region of space around the point minus 1 meter, comma 2 meter, comma 3 meter, comma, close the bracket, like this, write like this. If the potential in the region of space around the point minus 1 meter, comma 2 meter, 3 meter is given by V is equal to 10x square plus 5y square minus 3z square. If the potential in the region of space around the point minus 1 meter, 2 meter, 3 meter is given by V is equal to 10x square plus 5y square minus 3z square volt, comma. Calculate the 3 components of electric field. Calculate the 3 components of electric field at this point. Calculate the 3 components of electric field at this point. Calculate the 3 components of electric field at this point. So this is the problem. So they have given this is problem related to lecture number 5. It is numerical related to lecture number 5. The information related to this one, it is theory of this one is there in the lecture number 5. That is relation between electric potential and electric field intensity. Relation between electric potential and electric field intensity. See here what they have given. If the potential in the region of space around the point minus 1 meter, 2 meter, 3 meter is given by that is potential is given 10x square plus 5y square minus 3z square volt. Calculate the 3 components of electric field at this region. So that is given. So write given. So x is equal to minus 1 meter, y is equal to 2 meter and z is equal to 3 meter. And the potential is also given. And we have to find out component of the electric field along x axis, component of the electric field along y axis and component of the electric field along z axis at these points according to the question. Understood? So we know that electric field intensity E is equal to minus dV divided by dx or dV divided by dr, like this we have derived. So this can be done as, so component, that is x component, x component of electric field, 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 that is Ex. Ex is equal to dou V divided by dou x minus dou V divided by dou x. dou v divided by dou x. That is, you can write dv divided by dx also. Just if you write dou v divided by dou x means the y component and z components are constant. Dou v by dou x means the only differentiation with respect to x and y component and z components are constant, and v is given already here. So minus dou divided by dou x, substitute v, that is 10x square plus 5y square minus 3z square. Just I will solve this one completely. So if you differentiate this one with respect to x, only you can differentiate this one. Differentiation of 5y square with respect to x becomes 0. Differentiation of 3z square with respect to x becomes 0. Only you can differentiate this one. So therefore you will get minus 10 differentiation. So you know the formula of differentiation. Differentiation of x raised to n with respect to dx is equal to n x raised to n minus 1. You remember this formula. This is formula of differentiation. It is formula of differentiation. Differentiation of x raised to n dx is equal to n x raised to n minus 1. Understood? So here differentiation of 10x square. So 10 is constant. Differentiation of x square with respect to dx, it is 2 x raised to 2 minus 1. 2 x raised to 2 minus 1, that is 10 into 2 x raised to 2 minus 1. So this will becomes 10 into 2, 20. X raised to 2 minus 1 is 1. So this is minus 20x. So Ex is equal to minus 20x. And now the x value is given. X value is given. So x value is given as minus 1. So now substitute. Substitute x is equal to minus 1 meter. So therefore Ex is equal to minus 20 into how much? Minus 1. Minus 20 into minus 1. So it will become 20 Newton per coulomb. Newton per coulomb or volt per meter. Volt per meter. So this is answer. This is x component. Ex is completed. Similarly, you have to component y component. So that is y component. Y component. So it is Ey is equal to minus dou v divided by dou y. So Ey is equal to minus dou divided by dou y. So only y component, that is you can substitute all these things or instead only substitute this much, because differentiation of x with respect to y becomes 0. This cannot be, this differentiation becomes 0, this differentiation with respect to y becomes 0. So only substitute 5y square. So 5y square. So differentiation of 5y square, it is minus 5 constant outside. Differentiation of y square with respect to dy. Differentiation of y square with respect to dy. So you will get y raised to 2 into y raised to 2 minus 1. So there, that is we will get Ey is equal to, so it is minus 5 into 2, that is 10, minus 10 into y. So now substitute y is equal to how much? 2 meter. Shall I remove this one? I will remove this one. So now y is equal to, Ey is equal to, it is minus 10 into y is 2. So 10 into 2 minus 20 volt per meter. So this is Ey. It is electric field along the y-axis. This is component of electric field along y-axis. Similarly, now component of electric field along z-axis. That is z component. Z component Ez is equal to minus dou v divided by dou z. So z component how much it is? Minus dou divided by dou z into minus 3z square. Minus 3z square. So z is equal to 3, no? Okay. Remember that. So Ez is equal to. So therefore differentiation. So minus 3 into 2 z raised to 2 minus 1. So I will get minus, this minus is also there. it is also minus, minus into minus, it becomes plus. So 2 into 3, 6, 6 into z, and z is equal to 3. So therefore Ez is equal to plus 6 into 3. So that is 18 volt per meter. So Ez is equal to 18 volt per meter. So this is z component of the electric field. We have calculated the x component of the electric field, and we have calculated the y component of the electric field and z component of the electric field. That's it. Just you have to know the differentiation. See, if you have not studied differentiation, it looks a little bit difficult, but once if you study differentiation in mathematics, it all looks like very simple. So that's why don't be worried. Okay. Next, same type of one more problem. Next numerical. Write down the next numerical. This is for homework. This is for homework. Homework. In a Cartesian region of space. Write down. Homework. In a Cartesian region of space. In a Cartesian region of space, comma, in a Cartesian region of space, comma, electric potential. In a Cartesian region of space, comma, electric potential V. It is x, y, z. V of x, y, z is equal to ax plus bx square plus cy square. In a Cartesian region of space, comma, electric potential V is equal to ax plus bx square plus cy square, where a, capital A, B and C are constants, where A, B and C are constants. In a Cartesian region of space, comma, electrical potential V is equal to ax plus bx square plus cy square, where A, B and C are constants. You please stop. Find x, comma, y and z components. Find x, y and z components of electric field. Find x, y and z components of electric field at find x, y and z components of electric field at 1 meter, comma, 2 meter, comma, 0 meter. 1 meter, 2 meter, 0 meter. This is points. You please stop. This is numerical. So you have to solve on your own. You solve on your own. This is same way. Here A, B and C are constant like numbers, like 10, 5 and 3 in the previous question, like that. So you solve on your own, you will get the answer. So I will give the answer. If you want, I will give the answer. So answer for Ex. So answers, I will give the answers. Ex is equal to minus A plus 2B, like this, and then these all are answers that I am giving. Then Ey is equal to, so C value is 2, so minus 4, no, 2, minus 2C, okay, minus 2C, volt per meter. This is volt per meter, minus 2C, and Ez is equal to 0. So these all are the answers. So you will have to get. Understood? Okay. Okay. Next numerical. Okay. Next problem. Write down the next problem. Write it. You only know the number. An infinite plane sheet of charge density. An infinite plane sheet of charge density 10 to the power minus 8 coulomb per meter square. An infinite plane sheet of charge density. An infinite plane sheet of charge density 10 to the power minus 8 coulomb per meter square is held in air. An infinite plane sheet of charge density 10 to the power minus 8 coulomb per meter square is held in air. Is held in air. Give please stop. In this situation, how far apart in this situation, how far apart are two equipotential surfaces? In this situation, how far apart are two equipotential surfaces? In this situation, how far apart are two equipotential surfaces, whose potential difference is 5 volt. Whose potential difference is 5 volt. Whose potential difference is 5 volt. Question mark. See the question. An infinite plane sheet of charge density 10 to the power minus 8 coulomb per meter square is there, and we have to find the distance between the equipotential surfaces. Distance between the equipotential surfaces where potential difference is 5 volt. The potential difference between the two equipotential surfaces is 5 volt. So it is there is a infinite plane sheet of charge density. There is a very big plane sheet. A big plane sheet is there. So there is a two electric potential, that is potential points. So this is one potential point, this is one equipotential point. So distance between these two equipotential point, we want the potential difference between these two is 5 volt, and charge density on this plane sheet is 10 to the power minus 8 coulomb per meter square. Understood? So we know that solution, I am solving this numerical. We know that the electric field due to plane sheet, infinite charged plane sheet of charge density sigma is given by the electric field due to infinite plane sheet of charge density sigma is given by E is equal to sigma divided by 2 epsilon naught. This is the formula for electric field intensity. The electric field intensity due to infinite plane sheet of charge density sigma is given by E is equal to sigma divided by 2 epsilon naught. That is, the electric field intensity is there. Now let us take, let delta R be the distance between equipotential surfaces. Distance between equipotential surfaces, that is two different distance between two equipotential surfaces. Two equipotential surfaces having a potential difference delta V. Let delta R be the distance between two equipotential surfaces having potential difference delta V. Then we can write E is equal to delta V divided by delta R. V is equal to delta V divided by delta R. So E, that is nothing but electric field, is due to this plane sheet only. Here electric field is due to the plane sheet. So substitute this value, that is on substituting sigma divided by 2 epsilon naught is equal to delta V divided by delta R. So therefore what we want? We want the distance between these two plane sheets delta R. So therefore delta R is equal to, here I will write. So therefore delta R is equal to 2 epsilon naught delta V divided by sigma. 2 epsilon naught delta V divided by sigma. So therefore delta R is equal to 2 epsilon naught. Epsilon naught value 8.85 into 10 to the power minus 12 delta V, that is potential difference between two equipotential surface. These two are equipotential surfaces only, but they are separate and there is a potential difference. It is 5 volt. 5 volt that is given, and sigma is that is charge density. Charge density of this plane sheet, it is given as 10 to the power minus 8. So therefore delta R is equal to, calculate 2 into 5 10. 10 to the power minus 12, 10 to the power minus 11. 10 to the power minus 11 is 10 to the power minus 8 goes to numerator plus 8. So you can write 8.85 into 10 to the power minus 3 meter, or delta R is equal to 8.85 millimeter. 8.85 millimeter. So the distance between the two equipotential surfaces, the distance between the two equipotential surfaces is 8.85 millimeter due to this plane sheet. Understood? So this is how we can relate the things. Just now nothing. We have related this electric field due to the plane sheet and electric field intensity due to a potential difference delta V at a distance delta R, that is given by this formula. We know already. To combine and we will get the solution. Understood? Next problem. Write on the next problem. Next problem. Next one. The electric field in a region is given by, the electric field in a region is given by, the electric field in a region is given by vector E is equal to A divided by x cube vector I. The electric field in a region is given by, the electric field in a region is given by vector A is equal to A divided by x cube vector I. Come on. The electric field in a region is given by vector E is equal to A divided by x cube vector I. Come on. Write a suitable SI unit for A. Write a suitable SI unit for capital A. Write a suitable SI unit for capital A. Write a suitable SI unit for capital A. Cube list of. Write an expression for the potential in the region. Write an expression for the potential in the region. Write an expression for the potential in the region. Assuming the potential at infinity to be 0. 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 You please stop. So this is the question. Here what they have given. So they have given the electric field intensity, that is E is equal to A divided by x cube. A is some constant, whatever it may be. A divided by x cube vector I. Vector I means it is along the x axis. Okay. And then write a suitable unit for A. Write a suitable unit. We want unit for A, and then write an expression for the potential in the region, assuming. So now write the expression for potential and unit solution. So unit of A. So I will write like this is equal to. So change that formula. It is unit of E into unit of x cube. Unit of E into unit of x cube. And SI unit of electric field intensity is volt per meter or Newton per coulomb. Volt per meter or Newton per coulomb. So therefore unit of A will be, it is if you substitute volt per meter, and this is distance. X is nothing but distance, so x cube, therefore meter cube, so you will get volt meter square, volt meter square. This is the unit of A. Or you will get, or another one you will get Newton per coulomb if you substitute, Newton meter cube per coulomb, Newton meter cube per coulomb. It is Newton per coulomb into meter cube, Newton meter cube per coulomb. This is the SI unit. Write the SI unit is completed, and then write an expression for the potential. So now potential in a region is given by, potential in a region of electric field is given by V is equal to minus integration of vector E dot dr. That we have already solved in a region. So if you take coordinates, it is x, y and z. Potential at a point where coordinates are x, y, z is equal to integration of vector E dot dr from where to where? From infinity to x, y, z. That is coordinates. Electric field at a point where the coordinates are x, y, z is equal to integration of vector E dot dr, and from infinity to that point where the coordinates are x, y, z. That coordinates is not given, just generally they have given the electric field. So substitute that one and you will get the answer. So integration of vector E they have given A divided by, instead of dr you write it as dx. Dr you write it as dx because it is x axis, only along x axis, so therefore write it as dx. So vector A is nothing but that is vector E is nothing but A divided by x cube into dx from infinity to x, y, z. And now A is a constant, taken it outside. So A is constant, taken it outside, x cube, integration of x cube. So write it like x to the power minus 3 dx from infinity to x. Okay, x to the power minus 3 dx. Y, z components are not there, only x, so I am just writing x. So now integration, you know the formula of integration. Integration of x to the power n dx is equal to x to the power n plus 1 divided by n plus 1. Using this formula you can write minus a, that is x to the power minus 3 plus 1 divided by minus 3 plus 1. From where to where? From infinity to x. So therefore minus a, x to the power minus 3 plus 1 is minus 2. So x to the power minus 2 divided by minus 2 from infinity to x. Now substitute the limits and simplifying it, we'll get, so that is V is equal to minus a divided by minus 2. So first upper limit, so x to the power minus 2, that is x only, so 1 by x square, 1 by x square minus 1 by infinity nothing. So therefore V is equal to a divided by 2x square, V is equal to a divided by 2x square. So this is the expression for potential, this is the expression for potential in that region. Understood? This is the expression for potential in that region. So V is equal to a divided by 2x square. Understood the question? Simple. Okay. Next question. These are our questions on lecture number 5. That is relation between electric field intensity and electric potential and equipotential surface. All that things we have studied. I think it was in lecture number 5 only. So related to that I am solving. Okay. So next numerical. Next one. Write on the next numerical. This is little bit bigger. A uniform electric field vector E of a uniform electric field. Next numerical, write down a uniform electric field vector E of 300 Newton per coulomb. A uniform electric field vector E of 300 Newton per coulomb. A uniform electric field vector E of 300 Newton per coulomb is directed along negative x-axis, is directed along negative x-axis. A uniform electric field vector E of 300 Newton per coulomb is directed along negative x-axis. Pupil stop. Is directed along negative x-axis. Pupil stop. A, capital A, comma, B and C. A, B and C are 3 points in the field. A, B and C are 3 points in the field, comma. A, B and C are 3 points in the field. A, B and C are 3 points in the field, comma, having x and y coordinates. A, B and C are 3 points in the field having x and y coordinates. A, B and C are 3 points in the field, comma, having x and y coordinates in meter. Having x and y coordinates in meter, comma, as shown in figure. As shown in figure. Figure बाद में डालो. Later on you draw the figure. Just write on the question first. As shown in a figure. You please stop. Find the potential differences. Find the potential differences. Delta VBA. Find the potential differences. Delta VBA. Write like this. Delta VBA, comma, delta VCB. Delta VCB and delta VCA. Find the potential differences. Delta VBA, comma, delta VCB and delta VCA. Draw this diagram. This is x-axis and this is y-axis and this is the direction of electric field. Direction of electric field. They have given 3 points. This is point A having the coordinates 4, 1. And this is point B having the coordinates 4, 4. And this is point C having the coordinates -3, 4. Draw the diagram. Draw the diagram. So this line indicates electric field. You know that. This is electric field in the direction of negative x-axis as given in the question. This is x-axis and this is y-axis. This is 0. Okay. So A, B, C. 3 points are there. Okay. See the question. A uniform electric field vector E of 300 Newton per coulomb is directed along negative x-axis. Is directed along negative x-axis. This is positive x-axis and this is negative x-axis. A, B and C are 3 points in the field. A, B and C are 3 points in the field. A, B and C are 3 points in the field having x and y coordinates in meter. Having x and y coordinates. X and y coordinates, x and y coordinates, x and y coordinates in meter as shown in figure. Find the potential differences delta VBA, delta VCB and delta VCA. Understood the question? We have to find delta VBA, that is potential difference between B and A. Delta VBA means potential difference between B and A. You have to find delta VCB means potential difference between C and B. And delta VCA means potential difference between C and A. You have to find. So first delta VBA. Okay. See here. So it is B and A. So if a unit positive charge, see here, this is very important, and remember the theoretical points of this numerical also. Whatever the theoretical points or whatever the things I am telling, try to remember. This is important for CET also. If a unit positive charge is moved from A to B or from B to A, if a unit positive charge is moved from A to B or B to A, the work done to move the unit positive charge from A to B is 0. The work done to move the unit positive charge from A to B is 0. Why? Because the displacement of the charge is perpendicular to the direction of electric field. The displacement of the charge is perpendicular to the direction of electric field. Remember that? Whenever the displacement of the charge is perpendicular to the direction of electric field, then work done is 0. There is another way of remember this point, or else you can tell like this also. A and B, we know that we have the formula E is equal to minus dB divided by dr. We have derived. On that day, I told about this negative sign. What is the use of that negative sign? The negative sign indicates that the electric potential decreases in the direction of electric field. In the direction of electric field, the electric potential will decreases. So now, if you see A and B are at the same vertical position. Both are at the same vertical position. So therefore, A and B are having a same potential. A and B are having a same potential. That is, potential difference between A and B becomes 0. Why potential difference between A and B becomes 0? Because they lie on a equipotential surface. They lie on a equipotential surface. On that day, equipotential surface also I explained. Negative sign I explained like this. Okay. So 2 points which are vertical in an electric field and perpendicular to the direction of the electric field, that 2 points, between the 2 points, if we try a plane, that plane is called as equipotential surface, and then on the equipotential surface, this A and B lies on the equipotential surface, so therefore potential difference between them is 0. That is, delta VBA is equal to VB minus VA, but VB is equal to VA because VB, that is B and A lie on a equipotential surface. So therefore delta VBA is equal to 0. Delta VBA is equal to 0. Understood? That is, potential difference between B and A will be 0. That means potential at B and potential at A is same. So hence work done in moving a charge over an equipotential surface is 0. Understood? Or you can also tell like this: if the displacement of the charge is perpendicular to the direction of electric field, if the displacement of the charge is perpendicular to the direction of electric field, then work done on the charge or work done is 0. Understood? So next, second one, delta VCB, that is potential difference between C and B. And now first look at this C and B. First tell me which is at lower potential and which is at higher potential by using this negative sign. That what I told, by using the negative sign symbol. Using this negative sign, on that day I told which is at lower potential and which is at higher potential. If you see these points, in the direction of electric field, the electric potential decreases according to this negative sign. So therefore C is at lower potential and B is at higher potential. And a positive charge moves from higher potential to lower potential. A positive charge moves from higher potential to lower potential. Remember that? A positive charge moves from higher potential to lower potential. Whereas a negative charge moves, negative charge is not there. If it was there, a negative charge moves from lower potential to higher potential. A positive charge moves from higher potential to lower potential, and a negative charge moves from lower potential to higher potential. So therefore, if a positive charge, a unit positive charge is moved from B to A, then work is done by the electric field. See here, if a unit positive charge is moved from B to A, unit positive charge I am telling, the unit positive charge or positive charge is moved from B to A, then work is done by the electric field. Why? Because the displacement of the charge is in the direction of electric field. Remember this point? If the displacement of the charge is in the direction of the electric field, if the displacement of the positive charge, if the displacement of the positive charge is in the direction of the electric field, then work is done by the electric field. What if the displacement of the positive charge is opposite to the direction of electric field? If it was like that, if the displacement of the positive charge is in a direction opposite to the electric field, then work is done by the external agent. Remember that if the displacement of the positive charge is in a direction opposite to the direction of electric field, then work is done by the external agent. So now here this is higher potential and this is lower potential. So a positive charge moves from higher potential to lower potential. So work is done by the electric field. So now all these things are not required, just for your understanding I am explaining all these things. Okay. So now delta VCB. So delta VCB is equal to, we want, and we know that E is equal to minus delta V divided by delta X. Delta V divided by delta X. So instead of this, delta VCB. And delta X is the displacement between C and B. So if you write like that, then you will get, so it is, here on left, right, delta VCB is equal to minus E into delta X. Delta VCB is equal to minus E, and uniform electric field. And electric field value is given something 300 Newton per Coulomb, and delta X is the displacement between B and C. See the coordinates 4, 4, X axis coordinate 4, and this is minus 3, this is 4, this is minus 3, and the displacement between these 2 points will be 7 meter. 7 meter. So that is from geometry you can write delta X is equal to x2 minus x1. So 4 minus of minus 3, 4 minus of minus 3 becomes 7. So displacement is 7. So therefore it will become minus 2100 volt. So this is potential difference. This is the potential difference between B and C. Understood? Got the idea? And now next what we want? We want potential difference between C and A. CA, delta VCA. So now third one, that is CA, delta VCA. Delta VCA we want. So delta VCA. So now the charge is moved from C to A. Okay. So now the potential difference that is between C and A, I will write it as delta VCA can be done as VC minus VA, or this one delta VCB can be done as VC minus VB. VC minus VB is equal to minus 2100 volt, right? And delta VCA, VC minus VA. And since electric potential at the point A and electric potential at the point B will be same, that is VA is equal to VB. And therefore delta VCA is equal to VC minus VB. VA, instead of VA we substituted VB. So VC minus VB. And VC minus VB is nothing but, from here, VC minus VB is nothing but this one. So therefore delta VCA is equal to minus 2100 volt. Minus 2100 volt. Understood this formula? Understood this problem? Here, that is potential difference between C and A is also 2100 volt. That means potential difference does not depend upon the path followed. So work done in general we will tell does not depend upon the path followed, it depends only on the position. It is here and here and here and here, potential difference will be same. Understood? Got the idea? Okay. So now next problem. Write the next problem. Next problem, this is homework. Next problem is homework. Write down 3 points. 3 points. Homework. This is homework like this one. So whatever the number you only remember. 3 points. 3 points A, comma B and C. 3 points A, B and C lie on a uniform electric field. Lie on a uniform electric field. 3 points A, B and C lie on a uniform electric field. 3 points A, B and C lie on a uniform electric field. capital E, lie on a uniform electric field, capital E of 5 into 10 to the power 3 Newton per Coulomb. 5 into 10 to the power 3 Newton per Coulomb. As shown in the figure. Figure is there. As shown in the figure. As shown in the figure. Cupidist of find the potential difference. Find the potential difference. Find the potential difference between. Find the potential difference between. Find the potential difference between A and C. Find the potential difference between A and C. This is the question. Find the potential difference between A and C. This is the question. Draw this diagram. Draw the diagram. This is point A, this is point B, this is point C, and they are given like these two are vertical. Okay. And further they are given this as 3 meter. This has 3 meter. 3 meter, 3 centimeter. 3 centimeter. And this has 5 centimeter. This has 5 centimeter. Solve on your own only. You only solve. This is homework. This is same as just now what we have solved. Just now we have solved the numericals. It is similar to that. And the answer for this one is, I will give the answer. Answer for this one is comes out to be minus 200 volt. Minus 200 volt. That is the answer. Answer for this numerical is minus 200 volt. Understood? This is homework. See, we have to do the homework. If you are not able to do the homework, then you are not learning anything. You have to do the homework. Try it. You will get the answers. Try it. You will get. I am giving last answers also. So it is just like theory class only. I am teaching in the classroom only. Just like I will think. So I am giving homework. Keep on giving the homework. So try to solve all that homeworks so that you will get better. Okay. So next numerical we will solve in the next class. Time is over. So next class we will solve the numericals. See, these all are the numericals on lecture 5. We will solve numerical on lecture 6 and 7 also. Okay.